Hello students, this is Dr. Faizan Mirza. We are discussing how the voltage fluctuates across the membrane, and in this video we'll be discussing about how these changes are occurring, what's diffusion potential, what's the Nernst potential, and what's Goldman-Hodgkin-Katz equation. So starting off with the diffusion potential. What is diffusion potential? Diffusion potential, it is caused by the concentration gradient of an ion along two sides of the membrane. For example, the difference of concentration of sodium in ICF and ECF. This is the diffusion potential that we know that sodium is bound to enter the cell. If a cell is assumed to be permeable to just one ion at one time, which obviously it's not, but let's for simplicity's sake take an example that right now the cell is permeable for one particular ion, and we take the example of potassium ion or sodium ion, either one of them. Both are univalent cations, so we know that the concentration of potassium inside the cell is higher. C is for concentration, so concentration of potassium inside, I is for inside, is higher, whereas the concentration of potassium outside is lower. O for outside, K plus for potassium, and C for concentration. ICF and ECF being separated by the cell membrane. So let's suppose if the cell becomes permeable to potassium, we know that potassium will move in its natural way, and it will move into the cell, and as it moves into the cell, this outside becomes strongly electropositive. We know that the cell itself was having a resting membrane potential, which means the membrane was having a negatively charged inside and a positive charge outside. This is how the cells are at a resting state. But when the potassium ions moved from the cell, for example, if they leave the cell, when they leave the cell, the outside becomes more positive because more positive charges start to accumulate outside. Potassium ions are just moving down the gradient. At plus 91 millivolts, further entry of potassium will cease, so more potassium cannot enter. So that's where the equilibrium is established. No potassium will go out anymore. Now let's take an example of sodium ions. Sodium ion concentration inside the cell is low and outside the cell it is high. The cell is at resting membrane potential, negative inside, positive outside. If the cell becomes permeable to sodium ion now, we know that the sodium will move down its concentration gradient, and you can very well predict which direction it will move. So sodium ions move in down their gradient. When they move in, the electropositivity starts to build along the inside of the cell because sodium is moving inside. At plus 61 millivolts, further entry of sodium will cease. So this is the diffusion potential of sodium. This is the diffusion potential of potassium, and the values at which they stop. At plus 91 millivolts, further potassium cannot move. At plus 61 millivolts, further sodium cannot move. But you need to keep in mind where the excess positivity built up by the movement of potassium ion, it built up outside, and where the positivity builds up when sodium is moving, that was the inside. Because this brings us to the Nernst potential and the Goldman-Hodgkin-Katz equation. EMF can be measured in millivolts. The equation for EMF here for calculating in a certain cell is EMF is equal to plus minus 61 multiplied by log of concentration inside divided by log of concentration outside. Actually, just plus minus 61 multiplied by log, and concentration inside upon concentration outside, you take the log once only. The diffusion potential, which exactly opposes the net diffusion of a particular ion through a membrane, is called as the Nernst potential. So the reversal is the Nernst potential. Diffusion potential we have already discussed, so Nernst potential is exactly what reverses it. It is determined by the concentration gradient of that particular ion across the two sides of the membrane. The greater the gradient of that substance, the greater the tendency of that ion to move will be. and greater will be the nerve's potential. Assuming that ECF is at 0 potential or 0 millivolts, and the nerve's potential is the EMF on ICF surface of the membrane. So this is the assumption that we take. The nerve's potential can be seen, it's positive for a negative ion moving from inside to outside, because this movement promotes electropositivity outside the cell. Whereas the nerve's potential is negative for a positive ion which is moving from inside to outside. Here it will promote the electropositivity outside the cell. So this is the basic difference. You need to understand the movement, that whether it's a positive charge or a negative charge is moving, and the direction in which it is moving. If is it going from inside to outside, or is it moving from outside to inside. This cell here, you can see the cell membrane, ICF and ECF. The sodium potassium pump pushes 3 sodium ions out, 2 potassium goes in, ATP is broken to ADP, a resting membrane potential of minus, you can say negative values established along the inside. And when this is working, the values that we get for sodium and potassium concentration is this. The sodium is about 14 milliequivalent per liter inside and 142 milliequivalent per liter outside. Potassium on the other hand is 140 milliequivalent liter inside and just 4 milliequivalent liter outside. You can see the enormous difference in the concentration gradient of these ions. This is primarily because of the sodium potassium pump. If we take the ratio of sodium inside and sodium outside, this comes out to be 0.1, and the ratio of potassium inside and potassium outside is 35.0. Sodium and potassium ions can keep moving down their respective gradients if the membrane was permeable to those. And this occurs through their leak channels. Now, when a membrane is permeable to more than one ion at a time, which actually it is, at that point we say that the diffusion potential depends on the polarity of the charge, the permeability of the membrane to each ion individually, and the concentration of each ion on the inside and outside the cell. In this case, the EMF is calculated by this formula. EMF, which is in millivolts, will be calculated by using the same similar equation to Nernst potential, but here the equation is changed. This is called as the Goldman-Hodgkin-Katz equation. Now the Goldman-Hodgkin-Katz equation is used for calculating EMF when 2 univalent cations and 1 univalent anion is involved. So this is calculated by using the formula minus 61 into log of this particular value. Now what is this? We are taking concentration of sodium inside, dividing it with concentration of sodium outside, multiplying both with the permeability of sodium and permeability of sodium. This we deal with sodium. We add this to concentration of potassium inside, multiply by permeability of potassium, and divide by concentration of potassium outside and the permeability of potassium. Add it to the concentration of chloride, multiply by the outside and permeability of the chloride ion, divide by the concentration of chloride ion inside and the permeability of the chloride ion. The positive charges are placed in the numerator. Here, moving from the inside values are placed in the numerator, whereas the negative charge outside value is quoted in the numerator. Its inside value goes in the denominator. Similarly, the positive charges concentration outside is taken in the denominator. So this equation was derived by Goldman, Hodgkin and Katz. This equation is the basis of how our neurons work and how our muscles can contract and how the electrical changes can occur during impulse transmission and during the muscle contraction. That's it from my side. Thank you so much.